if I want to draw a dot structure for boron trifluoride, I need to think about VSEPR theory. So valence shell electron pair repulsion. The valence electrons are going to repel each other and force the molecule into a particular shape or geometry. And so we first start off by drawing the dot structure. So for boron trifluoride, I find boron in the periodic table. It's in group 3, so it has 3 valence electrons. Fluorine is in group 7, so it has 7 valence electrons. I have 3 of them, so 7 times 3 gives me 21. 21 plus 3 gives me 24 valence electrons that we need to account for in our dot structure. Boron is less electronegative than fluorine, so boron's going to go in the center like that, and the boron is bonded to 3 fluorine atoms. So I'm going to go ahead and put in those 3 fluorine atoms like that. So we just represented 6 valence electrons. So here's 2, 4, and then 6. So 24 minus 6 gives me 18 valence electrons left that we need to worry about. We're going to put those leftover electrons on terminal atoms, which are our fluorines in this case. Fluorine follows the octet rule, so each fluorine is now surrounded by 2 valence electrons, so each fluorine needs 6 more to have an octet of electrons. So I go ahead and put 6 more valence electrons on each of the 3 fluorines, and 6 times 3, right, is 18, so we just represented 18 more valence electrons, and so now we are all set. We've represented all 24 valence electrons in our dot structure. And some of you might think, well, boron is not following the octet rule here, and that is true. It's okay for boron not to follow the octet rule, and to think about why, let's assign a formal charge to our boron atom here. And so remember, each covalent bond consists of 2 electrons, so I'm going to go ahead and draw in those electrons in blue here. And when you're assigning formal charge, remember how to do that. You take the number of valence electrons in the free atom, so which is 3. From that number, you subtract the number of electrons in the bonded atom. And so when you look at the bonds between boron and fluorine, one of those electrons goes to fluorine, and one of those electrons goes to boron here. So we can see that's the same for all 3 of these bonds, and so now boron is surrounded by 3 valence electrons in the bonded atom. 3 minus 3 gives us a formal charge of 0. So remember, the goal is to minimize formal charge when you're drawing your dot structures. And so this is a completely acceptable dot structure here, even though boron isn't following an octet. Now, boron can be surrounded by 8 electrons, and so you'll even see some textbooks say, well, one of these lone pairs of electrons on one of these fluorines could actually move in here to surround the boron with 8 electrons, giving it an octet. And that's fine. That would give the boron a formal charge, and that's okay, and that might actually contribute to the overall structure of this molecule. But for us, for our purposes, we're just going to stick with this as being our dot structure here. So let me go ahead and redraw that. And I'm going to draw it in a slightly different way when we talk about our next step here for predicting the shape. So let me go ahead and put in our lone pairs of electrons here on the fluorine. And let's think about step 2. We're going to count the number of electron clouds that surround the central atom here. So remember, electron clouds are either the bonding electrons or non-bonding electrons, the valence electrons and bonds, or the lone pairs, just regions of electron density that can repel each other. All right, so if I'm looking at my central atom, which is my boron, I can see that here are some electrons, right? So that's an electron cloud. These electrons right here occupy an electron cloud as well, and then I have another electron cloud here. So I have 3 electron clouds that are going to repel each other, and that allows us to predict the geometry of those electron clouds around that central atom. They're going to try to get as far away from each other as they possibly can, and it turns out that happens when those electron clouds are on the same plane. So I'm going to draw a sheet of paper here, right, in a plane, and we're going to put our boron atom in the center, and here's one of our electron clouds, and then here's another one, and here's our third one here. So they're going to get as far away from each other as they possibly can. We call this shape trigonal planar. So let me go ahead and write that here. So this is a trigonal planar geometry of my electron clouds surrounding my central atom. And since we don't have any lone pairs of electrons to worry about on our central atom, we can go ahead and predict the geometry of the molecule as being the same here as the geometry of the electron cloud. So the molecule has a trigonal planar shape as well. Now, when we think about bond angles, right, so the easiest way to think about what's the bond angle for trigonal planar, or what would we predict the bond angle to be, right, you think about a circle, right? And since the electrons repel each other equally, you want to divide your circle into 3 equivalent angles. So 360 degrees divided by 3 is 120. So you can think about all of these bond angles here as being 120 degrees, since you can think about those electron clouds repelling each other equally. So we have a trigonal planar geometry with a bond angle of 120 degrees. So 3 electron clouds. Let's do another example of a molecule that has 3 electron clouds. So in this case, sulfur dioxide, right? So sulfur dioxide, let's count up the number of valence electrons. Sulfur is in group 6, so 6 valence electrons. Oxygen is also in group 6. 6 times 2 is, of course, 12. 12 plus 6 is 18. So we have 18 valence electrons for our dot structure. Sulfur is less electronegative, right? If you look at a periodic table, so sulfur is below oxygen, so sulfur is going to go in the center. Sulfur is bonded to 2 oxygens like that, so that just represented 4 valence electrons, right? Here's 2, and here's 2 more. So 18 minus 4 is 14 valence electrons left. All right, so we're going to start assigning some of those leftover electrons to our terminal atoms, which are our oxygens. Oxygen's going to follow the octet rule, and so therefore each oxygen gets 6 more electrons to give each oxygen an octet. So we go ahead and do that. So I just represented 12 more valence electrons, right? 6 on each oxygen. So 14 minus 12, right, is 2 valence electrons. So I have 2 valence electrons left over. And remember, when you have leftover valence electrons, you go ahead and put them on your central atom. So we can go ahead and put those 2 valence electrons here on our central atom like that. Now, we're not quite done with our dot structure because sulfur doesn't have an octet. As one way of thinking about it, you could also think about formal charge. Sulfur's formal charge is not minimized in this dot structure. So we need to share some electrons, right? So I could take, let's say, let me go ahead and make these blue here. So I could take a lone pair of electrons from either oxygen. I'm just going to say that we take a lone pair of electrons from that oxygen and move them in here to form a double bond between the sulfur and the oxygen. So if I do that, right, now I have a double bond between the sulfur and the oxygen. The oxygen on the right now has only 2 lone pairs of electrons around it. The oxygen on the left still has 3 lone pairs of electrons around it like that. And the sulfur still has a lone pair of electrons here in the center. All right, so if we assign formal charges now, let's go ahead and do that really fast. So we know that we have electrons in these bonds here. And so if we assign a formal charge to the oxygen on the left, let's do that one first. All right, so this oxygen on the left here, right? Oxygen normally has 6 valence electrons in the free atom, and in our dot structure, right, we give 1 of these electrons in blue to the oxygen and 1 to the sulfur. So you can see the oxygen is surrounded by 7 valence electrons. This one's a little bit hard to see, so let me go ahead and mark it there. So 6 minus 7 gives us a formal charge of -1 on this oxygen. And when we do the same formal charge for the sulfur here, right, we can see that sulfur is surrounded by 5 valence electrons. Sulfur is in group 6, so in the free atom there's 6. 6 minus 5 gives us a formal charge of +1. So we have a formal charge of +1 on the sulfur, formal charge of -1 on this oxygen. And even though we don't have a formal charge of 0 on these atoms, this is about as good as we're going to get in terms of this representation of the molecule here. And another thing to think about is the fact that I didn't have to take the lone pair of electrons from this oxygen, right? I could have taken the lone pair of electrons from over here, right, like on that oxygen, and that would just be another resonance structure of this. So I don't want to go too in detail about resonance structures and formal charge. We talked about those in earlier videos, so make sure that you watch them. But this is our final dot structure here. So let me go ahead and redraw it here. So this is one of the possible dot structures you can draw for sulfur dioxide, right, that fulfills our rules for drawing dot structures. So let me go ahead and put in these valence electrons here so we can see it a little bit better. All right, so I'll leave out formal charges now because we're just focusing in on geometry. We're concerned about VSEPR theory. So we have our dot structure. We go back up to check our steps for predicting the shape, and now we are going to count the number of electron clouds that surround our central atom. So regions of electron density, which could be valence electrons in bonds, so bonding electrons, or non-bonding electrons like lone pairs of electrons. So we look at our central atom, right, which is sulfur. And let's see if we can count up our electron clouds. So this is an electron cloud over here. There's a region of electron density, so we have one electron cloud. Over here on the right, this double bond, we can consider it as an electron cloud. We're not worried about numbers of electrons, just regions of them. And then for the first time, we now have a lone pair of electrons. Right, and this we can also think about as occupying an electron cloud, right? So we have 3 electron clouds, right? And we saw in the previous example that when you have 3 electron clouds, the electron clouds are going to try to adopt a trigonal planar shape. So I could redraw this dot structure and attempt to show it in more of a trigonal planar shape here, right? So let's go ahead and show it looking like this. Right. Once again, not worried about drawing informal charges here. So something like this for the structure. Let me go ahead and put those electrons in our orbital here so we can see that electron cloud a little bit better. And so once again, our electron clouds are in a trigonal planar geometry, so we would expect those bond angles to be approximately 120 degrees, right? So let me go ahead and put this in here. So approximately 120 degrees. It's probably slightly less than that, but that is what we would predict the geometry of the electron cloud to be. So let's go back up and look at our rules here, our steps for predicting the shapes of molecules. So we've done step 3, right? We have predicted the geometry of the electron clouds around our central atom, and now we go on to step 4 here. We're going to ignore any lone pairs on our central atom when we predict the geometry of the overall molecule. And so that now pertains to our example here. We're going to ignore that lone pair of electrons on the sulfur, right? We're going to ignore this lone pair of electrons when we're talking about the shape of the molecule. So even though the electron clouds have a trigonal planar geometry, we say that the shape of the molecule has a bent or angular shape. And so if you look at that, if you just look at the atoms, right? If you ignore the lone pairs and look at the atoms, right, you'll see this kind of bent or angular shape here. And so that's what we say is the shape of the molecule. So you could say bent, or you could say angular here. All right, so that's 2 examples of molecules with 3 electron clouds, and remember, it's not just the number of electron clouds. You have to ignore lone pairs of electrons to predict the final shape of the molecule.